Hello, my name is Michael Welch and I'm a researcher at the Danish Hydrocarbon Research and Technology Centre based at the Danish Technical University. I want to talk to you today about some work myself and my colleagues have been doing building geomechanically-based models of a fractured chalk field offshore Denmark. The field that we're looking at is the Cracker field, which is developed over a large salt pillow. It's been mapped out on seismic where it is about 8 by 5 kilometres in size and cut by a series of north-northeast, south-southwest striking faults. The main reservoir unit is the Danian age chalk forming the Ekofisk formation. This is generally a fairly low permeability chalk, but the production is enhanced by a series of natural fractures. We observe many of these fractures in the core, where we see two main types of fractures. Firstly, we see a number of small fractures, typically up to about 50 centimetres in size, often related to features such as stylolites or chert nodules, and these may provide a local permeability enhancement. We also see a few much larger fractures, often open, maybe cemented or with slicken sides, and these are thought to form large shear fractures that may be hundreds of metres in size and probably form major flow pathways. We can also see fractures on the borehole images, which we have from 7 wells in the field. Most of the fractures we see on the borehole images are conductive fractures, and these seem to correspond very well with the small fractures that we saw on the core. We see similar fracture densities between the borehole images and the core, and a similar distribution of fractures. We also see a few resistive or partially resistive fractures on the borehole images, and these seem to correspond much better with the large cemented or slicken-sided fractures that we saw in the core that may form the major flow pathways. The orientations show two main fracture sets. So firstly, we see a set of north-northeast, south-southwest striking regional fractures with a consistent orientation across the structure, and these may be related to the larger faults that were mapped out on the seismic data. We also see a set of fractures that with an orientation related to the salt pillow itself, so following the contours of the salt pillow or perpendicular to the contours of the salt pillow, and these are likely to be generated by the actual development of the salt pillow itself. We also have some high-resolution seismic data, and we used X-chroma and an ant tracking algorithm to try and highlight some of the subtle lineations within that seismic data. So when we take a slice through the centre of the Ekofisk formation, we actually see some very subtle lineations on this seismic data. Now, some of these seem to correspond quite well both in orientation and location with some of the resistive fractures that we saw on the borehole images. So it is possible that some of these lineations may represent fracture corridors or possibly damage zones around smaller shear faults, although obviously there's a lot of uncertainty here. So this is the information that we have directly from the field, and this was all described in a lot of detail in a recent paper by Arbo et al. In Marine and Petroleum Geology. So we now come on to the modelling aspect. So obviously, as we've seen, the fractures are key to controlling fluid flow in the Ekofisk formation, so must be included in any flow models. Traditionally, this has been achieved by either by modifying bulk properties to take account of the fracture porosity and permeability, the transmissibility multiplier approach, or by generating stochastically based discrete fracture network models. Now, these stochastically built models are created by essentially placing fractures at random locations in order to try and match the orientation and density of fractures observed in the wells. But we have typically little control on the fracture density away from the wells and no control on the fracture length and connectivity. And therefore, stochastic models often give poor representations of the actual fracture network and poor results when used in flow modelling. So we wanted to see whether we could build a more realistic fracture model by actually simulating the geomechanical processes of fracture nucleation and growth to build a DFN. So we start with the conceptual model. We're looking at a single planar homogeneous layer, in this case representing the Ekofisk formation, and we assume that initially it has a population of small circular microfractures, probably equivalent to the small chert and stylolite related fractures we saw in the core. As we apply a horizontal extensional strain to the layer, this generates a stress concentration around the tips of these microfractures, and they start to grow. Eventually they will reach the top and bottom of the layer, whereupon they cannot grow vertically, but they can continue to grow laterally, forming layer-bound fractures. Now, as time goes on, more of these fractures will nucleate and they will propagate until they start to interact. We can model two sorts of fracture interactions: stress shadow interactions, where two parallel fractures will terminate, forming a small relay zone, or intersection between perpendicular or oblique fractures. So the ultimate density distribution and connectivity of the fracture network will depend on the rate of nucleation, the rate of propagation, and the rate of interaction, which are all determined by the geomechanical properties and, most importantly, by the strain that we apply. Now, in the cracker case, there are two possible sources of the strain. Firstly, we can model an east-south-east, west-northwest regional extensional strain, which would correspond to the regional fracture set that we saw on the borehole image data and to the larger faults mapped on the seismic. We can use a boundary element method to calculate the local stress anomalies that will be generated around the seismic scale faults as a result of this regional strain. We can also model the strain related to, flexural strain related to growth of the salt pillow. And we did this using an algorithm that was developed by a team at Aarhus University, using a backstripping technique to calculate the flexural strain over time. And what we found here is that we generated a radial strain pattern, but the highest strains were seen not on the crest of the structure, but on the flanks of the structure. Now we can use this strain field to generate a fracture model, and the advantage of simulating the growth of the fracture network is that we can see how the fracture network develops through time. So, for example, in the early stages of the growth of the fracture network resulting from the flexural doming related strain, we see fractures develop first of all around the flanks of the pillow, and we see the orientation of the fractures following the contours of the dome. As we apply the strain over a longer period, we see the fractures will start to spread to the lower strain regions on the crest of the structure. We also see the development of secondary fractures connecting the primary concentric fractures, so forming two perpendicular sets of fractures. If we zoom in a bit closer up around one of the wells, we can see quite a good match between the modelled fracture network shown in dark blue and the observed resistive fractures on the borehole images shown by these light blue discs. We see quite a good correlation both in orientation and in the spacing between these fractures. And this applies over most of the structure, except near the faults. Around the faults, we find we actually get a better match in fracture orientation with when we use the regional strain with local strain development around the faults. So we see, for example, around these large faults mapped on seismic here in green and yellow, quite a complex fracture geometry induced by the local stress anomalies around those faults, and that matches very well with the observed fracture orientations seen on the borehole images. And just a reminder that the fractures we're talking about here are the large open slicken-sided fractures that we saw in the core. And this is an example where we see one of these fractures in the core, and again the orientation, at least in terms of strike, is very similar to the orientation predicted by the model. Obviously the dip direction is in the opposite direction in this case, but as a conjugate set of fractures we would expect fractures to form in both dip directions. We can also compare the fractures formed by the model with the what we see on the AntTrack seismic data. Here we see a bit more ambiguous results. So in some areas we see quite a good match both in orientation and in the spacing and the density of some of the lineations that we saw on that we see on the seismic data, and the density distribution and spacing of the fractures in the fracture network. However, in other areas the correlation is not so good. So, to summarise, we've shown that we can generate a discrete fracture network model that is consistent with the observed fractures on borehole images by forward modelling the fracture growth. The layer-bound fractures in this model represent the large cemented or slicken-sided fractures that are observed in the core and that are likely to form major flow pathways. The smaller fractures may represent the observed in the core may represent the seed microfractures that develop into these larger fractures. And the key to getting an accurate fracture prediction is to get the correct strain history. And finally, we've shown that the AntTrack seismic data may show some similar patterns to the modelled fractures, although there's more uncertainty in this case. So, thank you for your attention, and I'm certainly happy to answer any questions that you may have.